Hello, this is Dr. John, your physics and math professor, coming to you with another physics problem. This one is about Spaceman Spiff. As he's flying in his spaceship, he's flying at 250 meters per second straight this way, and then he fires a rocket, a photon torpedo, down 32 degrees from his horizon, and he fires it at 58 meters per second at this dangerous Xenon down here. What we want to know is at what velocity does this torpedo hit the Xenon down here. So what we have here is we have a pretty typical problem in vectors. I'm going to draw this out here for you again. So this vector here is 250, and then this vector over here is 58 at 32 degrees down. Remember the vectors, the important thing about vectors is that you keep the length the same and the direction the same. Otherwise you can move vectors around at your convenience in whatever way helps you to solve the problem. This isn't really helpful. Normally what we want to do is if we want to find the final vector, the final velocity, these are vector velocities. If we want to find the final velocity, what we'll need to do is we'll need to put the tail of one to the tip of the other. We can go either way. We could take this 250 and move it down here, or we could take this one and move it over to here. Let's take this shorter one and move it over to here. I'll draw it just the same, copying this. And this here also is 32 down here. And this is also 58. Now we have two vectors there. I don't need this one over here. I'll erase that. I've of course stretched this vector out artificially. It's almost the same length as this one on here, but in reality it should be about a quarter of this length. Don't let that fool you. I just did that so that we can see what we're doing a little bit more clearly. Now the next step is to say, what do we want? We want the resultant vector of this. So we want to add up these two vectors, which would be a vector like this. It would be from this tail to this tip. So we're really taking this vector here. This is V1. This vector is V2. This vector is V3. We're really taking V3, I could put those things, is equal to V1 plus V2. That's really what we're doing here. We're adding up these two vectors, but this is how we do it in practice by putting it on a page like that. So we don't need this because you know what we're doing here. Let's take a look at this. How do we find out this vector here? Well, there's a couple of different ways. I'm going to do this problem in two different ways. One is we're going to use the cosine law, which is sort of the way that you would naturally think of doing this if you've already taken that as part of your course. And the other one is to add up vectors. Both are completely valid. We're going to do it in both ways and show that you get the same answer no matter how you do it. So take a look at this triangle here that we have. We have a triangle with three sides. This is the side that we don't know. So this is the unknown velocity here. We know this side, we know this side, and if we knew the angle between them right there, that would allow us to use the cosine law. Because remember, the cosine law is just simply this. This is the angle C, this is the side C, the side A, the side B. It says if we know side A, side B, and angle C, we can get side C. And there's a very simple formula for that. I'm going to take that formula and write it over here. Well, maybe it's not that simple. It would be the length of C squared is equal to A squared plus B squared minus 2AB times cosine of C. Notice this length of this side is related to the angle opposite it, the cosine of the angle opposite, and the sum of these two sides. And in a way, this is sort of a takeoff of Pythagoras' theorem. If this angle was 90 degrees, I'm going to redraw this quickly here. If this angle was 90 degrees, C squared would be equal to A squared plus B squared. C squared equals A squared plus B squared. If this angle is 90 degrees, cosine is equal to 0, and cosine of 90 is equal to 0. This term becomes 0. So this term only comes into effect if this angle gets bigger than 90 or less than 90. This is like, sort of think of it as the universal Pythagoras' theorem that extends beyond just this being 90 degrees. And we're going to use this here because you notice this side here, this big V, that's the opposite side to this angle. And we know this side and this side, similar to what I drew up here before. Now you may wonder, how do we know this angle up here? This angle right there. That angle theta. Well, if you think about this, take a look at this over here. This line over here is 250. Here's the dashed line. Here's this vector. This vector is 32. What is this angle over here? Well, this whole thing will add up to 180. So this angle will be 180 minus 32. 180 minus 30 would be 150, so this is going to be 148. This angle here is equal to 148. Now we can use this relationship here to find the length of this. Remember, we're talking about a velocity vector, but we can add up anything. Acceleration, velocity, distance, we can add up anything as long as all of them are of that same unit. So let's take a look at this. We got the angle here of 148, and we've got the different sides here. I'm going to write this over here just for the sake of space. Well, maybe I can do this over here. Or I can call this v squared, this one here, is equal to the other two sides squared, 250 squared plus 58 squared, that's the other side, minus 2 times these two, 250, 58, cosine 148. Now I have everything here to calculate this. This, of course, is going to be probably a little bigger, I'm guessing, than 250. If you take a look at the shape here, probably going to be around 300, maybe 350 or something like that. Let's do this calculation. If I was doing this calculation, what I would do is calculate this first on my calculator, cosine 148, then multiply by these terms, write this all down on a piece of paper, then do these calculations and insert it in there. Don't trust your calculator or your brackets to save everything and do it all properly with bed mass. It's probably going to make a mistake and get you a funny answer. So if you can look up here and see, okay, it should be around 300 or 400, then we can do this calculation. I'll do this on my calculator. I'll be right back with the answer that I get. Equal to 300.8 meters per second. So that would be the velocity of this. Does it seem to make sense? 58 plus this. Remember, this one is going to be much shorter in real life, like this. So it's going to be just slightly longer than this. So this will be the answer that we get from the cosine law. I'm going to write the answer in here, and then we'll do this another way. So velocity, final upon impact, 300.8. Of course, we have two significant figures here, two significant figures here, two significant figures here. We should probably represent this with two significant figures as well. How would you do that? Well, you would say this is equal to 3.0, because now you have two significant figures, times 10 to the 1, 2. Now both of these figures are significant because you put that 0 in there. Here you have 4 significant figures. It's too many. So either of these answers, I would carry this answer until you come to the final answer, then write down this final answer. Now let's do this in another way. Let's do this by breaking this into components. Give me a second to erase this and we'll do that. All right, I'm back here with an erased whiteboard. Let's take these components here and divide them up into x components and y components. So here's the x and here's the y. We'll have to add the x component separately and the y component separately. If you can keep track up here, this one here is the easiest to keep track of. It's all an x component. It's going to be 250 in the positive x direction. That's all we've got from that. Then this one over here, I'm going to redraw this one a little bit. All right, I've redrawn this second component here, which is this component that's 32 degrees down from the horizon. It has two component parts. One of them is this one right here, which is the x component, and one is this one right here, which is the y component. If you can see that the sine of 32 is equal to this, I'm going to call this Vy and Vx. So in this case, the sine of 32 is going to be equal to Vy over this one, over 58. We can take the 58 to this side here, like this. And we're going to have Vy is equal to that. So this is the y component. That's this downward component. And it's going to be a negative 58 sine 32. This is going to be a negative 58 sine 32. We're making it negative because it's going downward. We're counting the up as positive and to the right as positive. So that's this component of this. In a similar way, the x component will be the cosine component of this. So that's going to be plus here, and it's going to be 58, just like here, times cosine of 32. This is also in the plus direction right here, so these are going to be added. This is going to be negative, but we're really not that concerned about the plus or minus because we're going to want the vector length of the final vector. Let me just add these up here for you in individual terms, and then I'll come back. All right, I've added these up, or I've done the multiplication. I've just redone this, 250, 250, and 58 cosine 32 is 49.2. Similar way I've done this, 58 sine 32 is 30.7. Think about this for a second. Which of these should be larger? Since this angle is less than 45 degrees, you'd expect that the x component would be larger than the y component. If this was 45 degrees, they'd be the same. Notice the x component is larger, so that makes reasonable sense. Now we need to add up these here as well, and we're going to get 299.2. Now we have the x component and the y component. Now we can use Pythagoras' theorem to add them up. Let me erase this. Here's what we're going to use for the Pythagoras' theorem. This squared plus this squared, and then taking the square root of the whole thing. I just did that on my calculator, and I got 300.8, which is the same value that we got over here for this. We should get the same value. Maybe it'll be off sometimes by a decimal or something, because it depends on how much we round it off as we make progress in the problem. I hope this helps with this problem. This would be the final velocity at which the photon torpedo hit the Xenon, and hopefully it did its job and it made the world safer for us. So that's a physics problem there for you. If this helps, like and subscribe. I will see you in the next one. Bye-bye.